Container security is not one scanner bolted onto a cluster. For SecurityX architecture, follow the unit of risk across the whole path: who built the image, where it was stored, what policy admitted it, how it runs inside a pod and node, what the orchestrator can limit, and what evidence returns to engineering after deployment. The image factory is where many container risks become permanent. Strong design uses approved base images, pinned dependencies, leased software, vulnerability triage, secret-free builds, SBOM generation, and signing or attestation. The goal is not to make every image perfect. It is to prove what is inside and decide whether that risk is acceptable before the image is promoted. A registry is not just a parking lot for images. It is a trust boundary between build systems and deployment systems. Architecture decisions include who can push, who can pull, whether tags are immutable, how old images expire, which signatures are trusted, which findings block promotion, and whether production can deploy only from approved repositories. Emission control is the checkpoint before a workload becomes a running risk. It can validate image source and signature, deny privileged containers, restrict host mounts, require resource limits, enforce namespace policy, and attach required labels. This is where engineering intent becomes enforceable cluster policy before scheduling. Once the container runs, architecture shifts from approval to containment. A hardened pod should avoid root, use read-only file systems where possible, drop Linux capabilities, apply Secump or AppArmor profiles, set resource limits, mount secrets carefully, and separate high-risk workloads onto appropriate nodes. The question is, if this container is exploited, what can it touch next? The orchestrator is powerful, so its boundaries matter. Namespaces organize policy, but they are not magic security walls by themselves. Use service accounts, RBAC, network policies, quotas, node pools, and segmentation by sensitivity. The senior design goal is to keep one compromised workload from becoming a cluster-wide identity, network, or data incident. Container security improves when evidence loops back to engineering. Runtime detections, admission denials, vulnerability drift, configuration changes, resource abuse, and incident lessons should update image baselines, backlog items, policy rules, and threat models. Without that loop, the cluster becomes a place where old assumptions quietly expire. Scenario: a checkout service team wants a fast release before a sales event. The image is signed, but a high-severity library issue has no available patch. The deployment also requests a privileged sidecar and a service account with broad secret access. A strong architecture response separates the risks, validate exploitability, document any image exception, deny the privileged sidecar unless justified, scope the service account, add network policy, increase runtime monitoring, and set an expiration for the exception. Concept check. A team scans container images, but clusters still accept any image from any registry, pods run privileged by default, and service accounts share broad permissions. What is the strongest architecture improvement? A. Scan images only and trust deployment teams. B. Block all releases until every finding is 0. C. Require trusted image sources and signatures. Enforce admission policy, reduce runtime privileges, segment workloads, and feed runtime evidence back engineering. D. Rely only on node firewalls. The best SIS airs